Hi everyone, this is Davide speaking, and in this video I'm going to talk about our paper Learning Action Changes by Measuring Verb-Adverb Textual Relationships. In this work, we are interested in understanding how an action is performed in a video. In other words, we aim to predict an adverb expressing how the action is performed. For example, in this video we could say that the action of mashing these potatoes is performed finally, but also gently, slowly, or completely. Let's start from the intuition on which we build our approach. Adverbs modify actions in different ways depending on the action themselves. For example, if we grind coffee slowly, we probably won't see any difference in the outcome of the action. However, if we grind it coarsely, we will see a considerable difference, especially compared to other adverbs such as finally. In order to learn adverbs, we want to learn this action change from the video. To do this, we cast the problem as a regression task. The problem is that we don't have a ground truth that quantifies the change we want to learn. In other words, we do not have a regression target. To define the action change applied by adverbs, we measure textual relationships between verbs and adverbs. The high-level idea is that we first build a minimal sentence S representing the modified action. We similarly build a negative sentence S tilde representing the action modified in the opposite way. Calculating the difference between S and S tilde, we have a proxy measure for the change the adverb applies to the action. We build S concatenating the verb and the adverb, for example, coat thinly, then generate S tilde replacing the adverb with its antonym, for example, coat thickly. Let's now suppose we have a text model G that receives a variable length sentence and outputs a fixed size embedding. We then extract text embeddings G of S and G of S tilde and measure the difference to capture how the adverb changes the action. More formally, we calculate the Euclidean distance between the positive sentence and the negative sentence and multiply this distance with the cosine similarity between the verb and the adverb. This gives us delta, which is the proxy measure of the action modification we were looking for. We can see in this figure what this delta looks like. For example, for adverbs finally and coarsely, we see a large action change for verbs chop, mince, mash, and grind. Now that we have our delta, we can define a regression target to train the model. To build such target, we simply set delta for the ground truth adverb, minus delta for the opposite adverb, and 0 for the other adverbs. This trains the model to distinguish opposite adverbs as much as possible, but it also adds a penalty for other non-antonyms adverbs with the 0 target. Let's now have a look at our full pipeline. We have a pre-trained video backbone which we use to extract video embeddings. We perform transformer attention to attend to the relevant parts of the video. For this, we use a text embedding as query. This text embedding is obtained with a text model that was jointly trained with the video model. Both the video backbone and the text model are pre-trained and we don't fine-tune them. We feed the projected features from the attention model to a shallow MLP, which we train with the mean square error loss using the regression target we just saw. We also evaluate a variant of the model where we cast the problem as a standard classification one. In this case, we use the cross-entropy loss and we don't measure any text relationships. Existing datasets for adverb recognition tend to be noisy and sometimes unreliable because they were not manually reviewed to ensure that the adverb attached to a video was actually relevant to the action. For this reason, we also collect a new dataset which we named Adverbs in Recipes, or in short. We source from cooking videos where adverbs modify actions in a significant way. We ask multiple annotators to manually verify the adverbs and the action in the videos, so our dataset is more reliable. We compare our model to two baselines. With the priors baseline, we just use the prior distribution of verbs and adverbs in the training set to make a prediction. With the S3D baseline, we test the same model we used to extract video and text features. We also compare against the previous state-of-the-art for adverb recognition, action modifiers. Finally, we compare three variants of our method. CLS, where we train the model with classification without any text proxy similarities. The reg fixed delta variant, where we use regression but fix delta to 1, so we discard any textual context. Finally, reg, which is the regression model where we use delta as defined earlier. Let's have now a quick look at the results. In the paper, we report several metrics. Here, for simplicity, I'll show only the weighted mean average precision for adverb classes. We evaluate 5 datasets, including our new air. On air and how to 100 million adverbs, our method outperforms the previous state of the art and the other baselines. We see that the regression baseline with fixed delta is our worst variant, which validates the idea of using learning targets that change according to each verb and adverb, which is what our reg variant does. On the remaining 3 datasets, however, we see that the prior baselines beats all methods or achieves very good results. The fact that a statistical method outperforms most learning methods suggests that these datasets are not very reliable, as it is difficult to learn action changes in these videos. In the paper, we elaborate more on this point, but in short, these results support our motivation of collecting a new dataset for this task. We also tried a setting where we do not pair adverbs in opposite meanings. In this case, to measure action changes, we simply remove the adverb to generate the negative sentence. The regression target is then delta for the ground truth and 0 for all other classes. We see that when we relax this assumption, our regression method performs even better. In the paper, we also lift another assumption, the availability of action labels during testing, which I won't include here due to time limits. To conclude, our approach achieves new state-of-the-art on adverb recognition, especially when we relax common assumptions. We saw that existing datasets aren't very reliable, so we collected a new one better suited for this task. Thanks for watching our video. You can find our code and our dataset by scanning the QR code here or visiting the GitHub link.